This lesson will describe the phenomenon of soil arching, which is a fundamental principle related to excavation stability during drilled shaft construction. An understanding of soil arching will help you understand how construction is accomplished with tools such as drilling fluids and casing that we'll talk about in subsequent lessons. Most geotechnical engineers have some understanding of the concept of earth pressure associated with retaining walls. So consider a wall which has magically been placed into the ground to replace the soil on the left without disturbing the soil on the right in its natural state. The pressure acting on the wall will represent what we call an at-rest condition, which is really the horizontal pressure in the ground before the wall was placed and associated with no movement. If we were to now push the wall into the ground, the soil, because of its shear strength, would resist the increasing pressure until some limit is reached, and we call this limit the passive earth pressure. If instead the wall were allowed to move slightly away from the soil, the earth pressure acting on the wall is reduced as the natural strength of the soil supports some of the load. If the wall moves far enough, the earth pressure reduces to a minimum level, and we call this the active earth pressure. A soil with greater shear strength results in less active earth pressure than one with lower strength. Therefore, a strong soil such as a dense sand with a higher friction angle produces less earth pressure force than a loose sand with a lower friction angle, and we certainly take advantage of this in the design of retaining structures. A three-dimensional excavation such as a drilled shaft hole can result in even lower lateral earth pressure forces than the active earth pressure condition thanks to soil arching. Looking now at a hole in plan view, we can see that as the excavation is advanced, an inward movement of the soil, just like for active earth pressure condition, can be resisted in part by the arching action of the soil around the hole. This arching action is a well-established principle in geotechnical engineering. The idea of soil arching actually goes back to a very famous experiment conducted by the father of soil mechanics, Karl Terzaghi, and reported in the first International Conference on Soil Mechanics in Boston back in 1936. Terzaghi described his trapdoor experiment, in which he slowly allowed a trapdoor to open in the bottom of a sand-filled box while measuring the force that the sand exerted on the trapdoor. As the door was lowered, the force from the soil diminished until a minimum value was observed, and Terzaghi attributed this reduction to the effect of arching of the sand above the door. He showed data and explained how the arching phenomenon resulted in even lower forces on the door for dense sand than for loose sand. Subsequently, there's been a lot of interest in this subject, and additional research such as that recently described from centrifuge experiments by Iglesias et al. In the journals has confirmed the general understanding of arching first described by Karl Terzaghi. This concept has broad application in civil engineering, particularly with respect to the design of culverts and tunnel support structures. Soldier piles and lagging is another application where arching around a vertical opening between soldier piles allows the relatively lower strength timber lagging to support the soil in between the piles. And of course, everyone is familiar with stone masonry and structures going back thousands of years, from Roman bridges to arches over doorways and windows. When we use a construction technique such as casing to provide temporary support for a drilled shaft excavation, we rely on arching to keep the stresses on the casing low enough so that the casing can be installed and extracted with the drilling equipment. Some factors that are known to affect the magnitude of the soil pressures beneath the soil arch include the depth of the overburden soil, which really relates to the magnitude of the earth pressures before arching occurs. The size of the opening. A larger hole requires the soil to arch further. The friction angle of the sand, as we know a dense sand arches better than a loose sand. And the relative inward displacement required to mobilize the soil arching forces and reduce the lateral stress. The relative inward displacement is related to the size of the opening. The understanding of this soil arching concept has an important application to drilled shaft construction. We know that there must be some inward movement in order for arching to occur. We know that there must be some lateral stress for cohesionless soil. Cemented materials such as rock may stand open for long periods of time without lateral restraining forces, just as a stone arch can be stable. Cohesive soil such as stiff clay may stand open for a short period, but we know there's a long-term tendency for clays to behave similarly to sands. So with our understanding of soil arching, we'll next look at drilled shaft construction techniques in more detail.